Again, our final speaker for this session is Andreas Engel. Andreas was one of the co-founders of the Maurice E. Müller Center for Structural Biology at the Biocentrum in Basel and a professor there until retirement in 2010. Andreas stayed active since then, in his own words, traveling the globe as an emeritus professor, and is also on the board at CryoRite, which is what he will talk to us about today.
So you have seen where I could be if I was not crazy in this nice hot skiing. But I really thank the organizers to give me the opportunity to be here. I'm overwhelmed with all the new stuff that is going on. It is such a beautiful science. So now I'm humbly presenting and try to transmit my enthusiasm to you for a different way to prepare cryo-EM grids. And you have heard about the nightmares. I can be very quick. The last picture on your right is actually what I think is also a nightmare, is when you are getting close to the thin ice you want to have, it pops away. So we have built a robot, and this is a delicate thing. It's a Ferrari. If you are not a good driver, you will just run it into the wall. But what it does is, now let me see. Yes, it deals with a sample with a pipette, and you will see all my talk is about this pipette. It writes on a grid here. It plunges the grid, which is held by this arm, into the liquid ethane. And there is a lot of space for additional features you can add up to this robot. And I have been working with that thing, and it was working, but we finally put it into a box because for safety reasons. Now what we do is shown here. We just write a thin layer. And the geometry are shown here. You can start with low speed, and when you pump out with a certain rate, you will make a thick layer, and then you increase the speed, and here the layer is thin. And that is very reproducible and gives you quite nice atlases. But it's a climb on a ridge. And it's really true. It's frightening. You thought that you have such a beautiful grid looking at this trace, and there are all empty holes. And then you think, oops, that you have done a good job, and now you have a nice looking square, but the ice is too thick. So whatever you do when you make a thin layer, you have somehow to find a balance between evaporation and initial layer thickness. It doesn't matter whether you spot or blot or CryoRite. So we have done a lot trying to improve this, but we are not at the end, but we can make it perfect. And then, of course, you have the usual stuff like you should have a good flow discharge, and you have good vitrification. Now, the point of all is we need 1 million picks to make a structure. You can calculate that this is almost nothing. And of course, the picture on the left is just almost a 2D crystal. So you could do something else in single particle. This here is a calculated sort of what you would like to have, distribution of particles, and this is real life. And anyway, the point I try to make, when you write a grid with something like a nanoliter or so, you have more than enough. Basically 4 orders of picks you could do if you could. Now, anyway, this robot, as you have seen, is quite a machine. And what really counts here is the mechanical accuracy, because if you have a gap variation that is too high, you will get uneven grid writing. And on the other hand, you want to have pumping, which is really reproducible. What you see between the red bars is a nanoliter. And you see it's reproducible to a small fraction of a nanoliter. So with those ingredients, you now can write the grids, as you have shown just before. And it was Wim Hagen who told me, hey, you have a great machine, but you have to prove by preparing liposomes. And then I thought, okay, no sweat, we do it. And then I thought the liposomes were shredded by the writing process, by the shearing forces during the writing. But that's not the case. And you see, then we started to do code writing, and that makes a big difference on evaporation. And here you see the liposome as they should be. So now I'm pushing this picture of evaporation while you do your job, plotting or writing or spotting. And we built a little interference camera. And there you can see the effect of evaporation. You just count the fringes, 4 or 5 fringes per second passing by. That corresponds to something like 0.5 micron per second. And on the left side is a very simple graph of what you write. First, you write thick, that's the blue line on top, and then you speed up, and the spiral gets thinner and thinner. And at the same time, of course, you have evaporation from the beginning of your writing to the very end when you plunge. And that gives you somehow an average. And you can see in this calculation, which is close to reality, you get layers which are just below 0.5 micron in average. Of course, this is just in average and is not what you see. But as you can see here, we have made many, many grids. We see in the atlas quite nice characteristic traces here. You don't see the spiral because you have adapted the geometry. And I wish to point out, so this is the B2 guy. And we were very close to dew point, cooling the grid. We had about 40 or even more good looking squares. When we went into the squares, we had less than 10% holes, as you can see here. And this is what the machine can do. But now, you know, the nightmare is the air-water interface interaction. And this is really something that drives all of us nuts. And there are different possibilities. I give you here a multi-layer writing option. And we have done it with a peptide, but you can do it. And this is a program we now have in progress, I want to say, which is optimization by writing the first layer with some additives, detergent, surfactant, something. And it works like this. You see the first nanoliter is written, and now the second layer comes. And you see this very nice particle distribution. In this case, it's not hard proven, but the peptide saturates my carbon film. So not everything is running onto that carbon film, but I have many particles as they should be in the hole. All right. So, you know, step by step, we got more bold, and we said, hey, we could write multiple samples on the same grid. The start was, can we just do it by line writing? And this is, as you can see here, on the left is a EPU characterized grid. We have some artifacts due to the wettening with the pipette, which was quite clean at the beginning. The idea was that we do different thicknesses. That is in the red box, just different volume. The last stripe should be the thinnest, and it is also the shortest, so that we can immediately identify which line is what. And you can see it should be half a micron, and the other one, the first one should be actually 3. However, they are all equal, and that is now, you see the robot does what you program, and it can do that very efficiently. You see one little stripe written after the other, but now from the data I have, I can make a plot, and you can see it measure evaporation rate, and this is very simple. It is post sample prep. And as you have seen, our interferometer will do it pre-sample prep. And then when we know that, we can dial in the rate we have measured. So you can write grids with so little, it's still orders of magnitude more than you want. But anyway, who cares? You have so much proteins from all your super protein chemists. So you just do the normal way of sample prep. But what I'm enthusiastic about is you have new possibilities. Just the multi-layer writing or multi-sample prep, you will see more of that. But here is a miniaturization of the magnetic trap purification. And the idea is that you have a bead, you have a link which is UV breakable, you have the nanobody or the fab, and here is what you fish out. You incubate and you suck in this material, and once it's trapped here, you can wash out what you don't want. Once you have washed this out, you separate, and you make a volume separated by little air bubbles, and then you break with a UV flash, and now you can start to write. And here you see the pipette, and those are the magnet-driven pole pieces, if you wish. And this now looks like that. You go into the incubated bead. You start to suck up the beads, and you see how in the center here, the beads start to accumulate. Now you have to do your core to get the washing done. And in fact, you now see the beads again here, and you see the washing, and soon the bubble will come down, which is then the top limit. Now you want to get this thing away a little bit so that you can do the pumping and writing. And at this point, this is all hand operation. It will be all automated. You have to shake up the beads a bit so that when you give the flash, the UV can actually break, and then you just can move away the beads, and now you're ready to write the grid. So another thing is to write more than one sample on a grid. Now the thing is, initially I thought we would just make 4 or 5 layers, each one like a nanoliter, and then just push it out. The silly thing is, of course, at the wall of the pipette, you have things sticking. So now you have to wash, and you see, this is what we got here. There was the first experiment. I would like to have 1,000 repeated, but day has 24 hours. And you still have enough nice grid squares. And here you see the last sample sucked in, middle one, and this is the first. And so this is showing no cross-contamination, but also no sample because it was aggregated protein. The process is you start with a clean pipette and you go, and here is 20 nanoliters. You have 1 nanoliter, and that one is written on a stripe. You have to go wash. And now into the next one. And well, yeah, this is the next stripe. Washing again, and you go, and the last sample is picked up. And you can see the nanoliter just ready to go on the grid jug, and that's it. So what I'm dreaming of is just to pick up a cell. Thomas has done the cell blasting using ITO-coated pipettes. I think we can modify the protocol a bit and actually suck in a cell and letting it being blown up by osmotic shocking. And then you have a shredded cell and you write out, and there is a certain cohesion in many multi-protein complexes within the cell that will not be shredded because the forces are so minute at such small scale. And then you would go, and you could also observe, if you have a fluorescently labeled protein, where is what. And you just write it out, as you have seen, in a thin layer, and you go and do tomography. So my summary, well, I don't have to say much. You can see, you see, we are at the beginning of something. And I'm sure that we can solve many problems which are on the technical side to get well-preserved proteins, get rid of air-water interface artifacts. There is plenty of literature about detergents or other things that are useful. And we then would move on to go to organelles in the cell, where you just go right directly onto imaging by tomography, such entities. I wish to thank all who have contributed. It is Thomas Braun who has started the whole project in his team, and it is my son who converted from a fantastic theoretical physicist to a financial analyst, and who provided the money for this startup. And I thank you for your attention.
Thank you very much. I think I'm going to ask the first question, I think. So you mentioned a couple of times the importance of the grid, both its reproducible hydrophobicity, its flatness. So does it work with different grid substrates, and is copper carbon the best combination?
All right. So we have not tried every grid. And I don't know, the copper grids are really quite fragile. They are usually not flat. They are already bent when you pick them out of the box. And if they are too much bent, they will crash. So basically what you have seen is that, and this is okay. Next step is to try out the molybdenum grids, which will be stiffer and flatter. So this is interesting. The next is to try out the hexa gold, which are really also highly precise. There is a trouble with our interferometer. We cannot really use it. That's logical. And what doesn't work, what I had high hopes, was the silicon grids. Silicon nitride grids, ultra flat, very precise, but they are pieces of glass and they are not easily handleable with the tweezers or with the gripper.
Okay. Yeah, I think so. I think there's still a lot more grids to try. I've seen, I don't know, the amorphous nickel titanium, the new ones from Den Solutions, the silicon with a thick window.
Yeah,
I think it's very, the field is big now in grids.
The carbon flat are good, and lazy grids are good. for what liposomes require. Yeah.
That's great. Thank you. Is there any questions? Go for the back.
Hi, I was wondering if you considered suspension cell culture. If you could disperse that of the grids as well. I don't know if that is at all applicable.
Well, there are many ideas about that, so that you would grow cells on a grid. You need to make a special rig for that, but this is just the usual type of microfabrication. We will do that, so that the cell would grow on the grid with a very special environment, if that is the question.
No, more like the cells that are not adherent to the grid, but rather the ones that can be cultured in media, right? So I imagine you could also apply them in a similar fashion, potentially.
I think you just have to suck away the liquid, and surface tension will flatten your cells. But this is really up to experimentation. But that can be done, yes.
Thank you.
Yeah, just across.
Hi, thank you. Have you ever tried these with nano microcrystals? Dispense them and then put ligand, and I assume you find a way to remove the excess liquid, something like that.
I will just invite you to the lab, because the thing is, we have done this, 3 of us together. Now we are a little bit more, and as I said, there are so many ideas. I'm sure the microcrystals would be a very interesting thing, because of course, when you start blotting, you have all the microcrystals on your blotting paper. And with this method, you have just made the layer. And yeah, please just drop a note, and I will spend happily days with you to get this going.
It's a generous offer. Is more questions? Oh, yeah. Kyle.
Hi. Is it possible, and are there any plans to use those interferometry measurements to provide a thickness map when you come to the microscope to direct where you collect data?
Yes. So there are 2 ideas. One idea is simply to make the measurement, as you have seen, just counting how the fringes go by. And there is now a software engineer taking care of that. So you would start the morning by rigging up the machine, getting it equilibrated, and then measure for those conditions exactly what the rate is. And then you put this value into the operating system, which tells you, aha, you have taken those parameters, you will get 0.5 micron thickness in certain areas. That is one idea. The other idea is to design a slightly different one with 2 wavelengths, so that you're not just counting rings passing by, but that you get an efficient, effective thickness measurement. And possibly we'll do that then on the frozen grid.
How accurate do you think it could be? How accurate do you think it could be?
Well, the fringes, they go by lambda quarter of 532 nanometers. So it is of the order of 100 nanometer by the whole fringe black to white. So I think it can be quite a bit more precise.
Thank you.
Okay, well, if there's no questions in the room, and I see that there are none on Slack, I think. So we shall just thank Andreas once more. Thank you very much.